Okay, last week we talked about checking if an infinite series converges by looking at the limit of the sequence of partial sums, and we talked about two special series where we can determine if they converge and actually find the value of the series if it converges, and those were geometric series and telescoping series. But for most infinite series, we can only tell if it converges, not what the value it converges to is. And so we're going to talk about some tests that we can use to determine if infinite series converges. And the first of those tests we're going to talk about in this recording, which is the divergence test. And then the next recording, we'll talk about the integral test and some other special series. Okay, well, one important and special series is the harmonic series. And the harmonic series looks like it's the summation n going from 1 to infinity of 1 over n. So it's 1 plus 1/2 plus 1/3 plus, etc. forever. So the question that comes to mind is, does this series converge? And so all we know so far is about partial sums, so let's see what the partial sums tell us. So the first partial sum is 1. The second partial sum is 1 plus 1/2, which is 3/2. The third partial sum is 1 plus 1/2 plus 1/3. Remember, the shortcut is to just do the second partial sum plus 1/3. And so that gives us, it sure does. That gives us, 11/6. The fourth partial sum is just the third partial sum plus 1/4. And that gives us 25 over 12, if you do the calculation and reducing. And the fifth partial sum is the fourth partial sum plus 1/5, which is 137 over 60, and so on and so on. So the kth partial sum is just the summation and going from 1 to k of 1 over n. So we have 1 plus 1/2 plus 1/3 all the way up to 1 over k. Okay, so what do we see with these partial sums? Well, it looks like they're increasing because we start at 1, then we get 3/2, which is 1.5. We're getting close to 2, then we pass 2, and so it looks like the partial sums are increasing. That's what it looks like. And just looking at these first several partial sums, it's not clear if it's bounded, right? So, I can't tell just by looking at it. Can you? So, I can either A, leave you in suspense. Nah, I won't do that. Okay, so in fact, it is not bounded. So it is not bounded, and we will see that later, But anyway, so since the sequence of partial sums is not bounded, that tells us that the harmonic series does not converge. So the harmonic series pops up now and again, so it's good to keep in mind that it does not converge. And we will check this out again later and actually prove, verify, whatever word you feel like using, that it does not converge. Anywho, the first and easiest of the convergence tests is really the divergence test. So we know that if a series converges, the limit of the terms is 0. But this is equivalent to saying that if I'm looking at the limit of the terms of a series and it's not 0, then that series has to diverge. But you have to be careful. And the reason you have to be careful is if the limit of the terms of a series is 0, it doesn't mean that the series converges. We just saw one that didn't converge, the harmonic series. So keep in mind that just because the limit of the terms is 0 does not mean the series converges. Okay, so let's do some examples to illustrate the divergence test in action. Notice that the divergence test will only be able to tell us if the series diverges, but the test can be inconclusive. And if the limit of the terms is 0, then the test is inconclusive. So, without further ado, let's look at some examples. Okay, so here, right, the terms of the series are these 3/2 to the k power. So if we take the limit as k goes to infinity of 3/2 to the k power, what do we get? Well, we get infinity, right? Because 3/2 is bigger than 1. So when we take increasing powers, and we already knew this, by the way. We knew the series diverges, so the series diverges. How did we know the series diverged? Well, we knew the series diverged because it is a geometric series. Right? Remember, if we have r to the k, and here r is the 3/2, which is bigger than 1. Oh, all right, the next one. Now, pretend we don't know anything for a minute. So we're just looking at this series, and we see that here a sub n is 2/3 to the n. And what's the limit as n goes to infinity of 2/3 to the n? I'll give you a second to think about it. If you said 0, then you win the prize. And since the limit is 0, that tells me that the divergence test is inconclusive. Do we know whether or not this series converges from another way, another method? Right? We do. And in fact, if the divergence test is inconclusive, that would mean that we actually would need to use another test. So, can you tell me what, well, I guess you can't actually tell me, but pretend you're talking to me, and you can shout out the answer to the screen. Hopefully you see that this is a geometric series. Geometric series with r equaling 2/3, which is less than 1. So that gives us convergence. Yay! So we got a couple of winners. Alright, now we'll look at some ones that are not going to be as much fun for us. Alright, so here. What are my terms of my series? If you said a sub k is equal to 1 over square root of k, you were correct. And what's the limit as k goes to infinity of these guys? Come on, y'all know it's 0. Don't play. So what does that tell us? That tells us the divergence test is inconclusive. What? How not helpful is that, huh? So the divergence test, easy but not always super useful. By the way, later, and by that later I mean next time, we will absolutely see that this series diverges. Boom. Alright, one more fun and exciting example. So I'm sure you all know how to check the terms of the series. But what is the limit as n goes to infinity of the terms of the series? You know what we need to do, right? What do we need to do to find this limit? We're going to divide the numerator and denominator by n, if you don't mind. And so if we do that, we're going to see that the limit as n goes to infinity, we get of 2, we get what I wrote. We get what I wrote. And that limit is 1/2, which is not 0. So that tells us that the series diverges. Dun, dun. And that's where the divergence test really gives us a boost. All right. Now you try one. I will... Well, I guess I don't actually have to wait. You should pause the recording right now. Just pause that there recording. And you take a moment and figure it out. And then put back on the recording. And you will see me work it out. So pause. All right. So we see that the terms of the series are 1 over n times n plus 1. And without even thinking about it, we know that this limit is 0, so the divergence test is inconclusive. So with respect to what I was asking you to do, we know the divergence test is inconclusive. We could do this another way, though. In fact, I think we did look at this one last time using partial fractions, and it's a telescoping series. But just from the perspective of the divergence test, you get nothing. All right, next time we will work on the integral test. Stay safe, everybody.